Okay, at this point, we're ready to reach our final destination for a circuit that serves as a memory element. And that final destination is the D flip-flop. So before, we had an SR latch and we had an S bar, R bar latch, and from that we built up a data latch. Now what we really want is a data flip-flop. And the difference is that what we want to have happen is we want to have a system clock that will time everything within a sequential circuit, okay? And so it turns out it's problematic if the timing occurs across the whole upper period here of the clock edge, the clock cycle. It would be better if we could just have changes happen or initiate things to happen on the clock edge, all right? So you see this is an edge because it goes from a 0 up to a 1. Now I show this as an infinite slope increase, all right? There's really a time period that it has to have happen before it can make this transition, but we're having this level of abstraction where we assume we go from 0 instantaneously up to 1, and that's our synchronization time for the clock edge. All right, so how would we build that kind of circuit out of what we have so far? Well, the answer is we can use D latches, and if we pair these in the right way, one would be for capturing the input, and the other is to pass that captured input that only is captured right at the edge and pass that on to the output, where you ignore anything else that might happen during the positive part of the clock cycle. Okay, so at this point, we're ready to build that. And so what I want to show you is in this infographic, you can pulse the clock. So look what happens. I have D set to 1. I have clock set to 0. Let's make this change. Q is already a 1. So if I make this to 0, all right, and then I pulse the clock. So notice right now, that's a 1. When I pulse the clock, it's going to open the latch and read that 0, pass that 0 to here, and then on the other edge, okay, the output latch opens here. That then passes that 0 on to the output. All right, so let's watch it one more time. Let's change this to a 1, pulse the clock. Notice what happens when I pulse the clock, okay? It's going to capture that 1 and pass it on through to the output. All right, one more time with a 0, pulse the clock, okay? At this point in time, D is equal to 0. So notice what happens. As I'm at the 0 part of the clock. The capture latch is open. So as I pulse this, the capture latch is transparent. So it's just following along what D should be because that's at the 0 edge of the clock. And then when I get a clock edge, all right, when I get a clock edge, that 0 is captured and pushed on through to the output. All right, so you have this dual latch situation where it's latching on the bottom part of the clock cycle for the capture phase, and then for the output phase, as soon as the clock goes high, it passes that on through to the output. All right, so the effective operation of this is that everything is synchronized only on the edge of the clock. Anything that happens in here will not change, okay? So one thing that's important to understand in a digital logic course is the difference between a flip-flop and a latch, okay? So I have this graphic here, and there's a chance for you to try it. So you go in the try it stage, and you can hide the outputs and make a guess at what everything should be. So you can work it out and then reveal the answers. All right, so let's go back and talk through what's happening with a timing diagram that illustrates the difference between a latch and a flip-flop. Okay, so let's first consider the case of a latch. All right, so here's the data input. All right, so you see things changing here. And what we know about a D latch is that when the clock edge, all right, so think of the clock as now the enable line on the D latch. When the clock is high, the D latch is transparent. So the output is just going to mirror. Notice this shape is the same shape as this. All right, so for the latch, it's going to mirror during the positive clock cycle. And then as we leave, as the clock edge gets unenabled, okay, it's going to latch. It's going to latch whatever the output was at the other side of this and hold it down at a 0 for the rest of this the 0 portion of the clock. All right. Then in the next enable cycle, when the clock is 1, it's going to follow. All right. So it's following the output is following the input. And then as we go to the 0 part of the clock, it latches that on. Okay, so you can see how that works. All right, contrast that to a flip-flop, where a flip-flop, the only thing that can change is right at the rising edge of the clock. Remember, we made it edge sensitive instead of level sensitive. All right, so what I do to look at the analysis for a cube flip-flop, I look at what D is right before the edge. So right before the edge, this value of D is a 1. So right after the edge, that just gets held. And it gets held throughout the whole clock period. All right, so the next instance, right before the edge of the clock, it's a 0. So it's going to follow that 0. Right before the edge of the clock, that's a 1. So it's going to follow the 1. And that's how you get the analysis for the Q flip-flop. So you can see they're definitely different circuits. You get different outputs for the same input. All right, so what I'd like you to do is try this. We're going to walk through some of these in class. This is something that shows up on exam problems. I want you to understand the difference between a flip-flop and a latch.